All right, so wrapping up chapter 1 with section 1.7, linear and absolute value inequalities. So we're finally going back over interval notation, even though we've kind of talked about interval notation throughout the course. The textbook likes to use both interval notation and set builder notation, which is like fancy inequalities, to talk about different intervals on a number line. So we've got this entire table here to show you how you would write in interval notation, set builder notation, and graph notation, the different ways of talking about a set of numbers. What I mean by a set of numbers is if we're trying to say between A and B, but not including A and B, that's what the parentheses mean, we could say that in interval notation. We can say that in set builder notation. Notice that all of these just have X and then a bar, which is the math phrase X such that. So it's X such that A is less than X, which is less than B. But graphically, we're just saying take every number in between A and B, not including A and B exactly. If we wanted to include A and B exactly, we would change the parentheses to brackets. Does that sound familiar? And we put the line underneath the less than signs to say less than or equal to. And on our graphs, we would change the parentheses to brackets. Now, here's the thing. When you've done this in other classes, I'm assuming you're like, wait, Miss Quigley, didn't we have like open circles and like closed circles? You sure did. This is the same thing as open and closed circles. The textbook that we use, though, instead of a closed circle, we'll put the brackets on the number line. And instead of an open circle on your number line, we'll put the parentheses on the number line. So if you notice, what you probably did before in another class, this would have been open circle, fill in, fill in, fill in, fill in, fill in, open circle. Same vibe. We're just going to use parentheses and then brackets. But what we're saying with these intervals is that all of the numbers in between A and B are a part of my solution. So I like to color these in like fun colors because it's just way more fun. So like, boom, all of these numbers are a part of my answer. But then for the bracket ones, I'm also going to include the bracket because A and B are a part of my solution. Now we can mix and match these symbols where it doesn't have to be just double parentheses or double brackets. You could say it's less than or equal to A and then just less than B, so not including actual B. You could vice versa that where it's not exactly A but bigger than A and exactly equal to B, all the way up to exactly equal to B. Now these four are pretty much the same, right, except for endpoints being included or excluded. But then we can get to the ones that go off the number line to infinity. So in interval notation, we would actually see the infinities. Yes, we see the infinities. Notice that in set builder notation, are there any infinities? No. So what you can do is write it as an inequality with the infinity showing, and then just erase the side of the inequality with the infinity sign, and then boom, you're left with what you need. So this number line here, which is saying, I want you to start at A, not including A, and go all the way to infinity. And I like to aggressively throw my arrows to the side because it's just more fun, right? Or we could say X is greater than or equal to A, which means that we're actually including A this time. Let's say that our endpoint at the top of the number line is included and we start at negative infinity. This would be considered X such that X is less than B, or X such that X is less than or equal to B if we're including that endpoint. This was a really janky looking arrow, so I'm going to fix that for myself. Wow. Now, of course, and we know this one, if we're going from negative infinity to infinity, that's the entire number line. In set builder notations, you can still write it as X such that X is a real number, but you probably won't. What does this mean? All real numbers. Totally fine. Say all real numbers. But on a number line, we would literally color from negative infinity to infinity. So it's the whole number line. That means every single number works for this solution. Now let's make sure we understand how these sets look on a number line and eventually how we can combine sets on a number line before we get into actual inequalities. So we're going to express each interval that's given A, B, and C in both set builder notation and a graph notation. Now this first interval is from -1 to 4. Let's first do the graph because it might be easier. So what I want you to do is put the parentheses that you're going to use around -1. Because we're saying we're going to start here but not actually include -1. And we're going to go all the way to 4, and 4 is included, so we put the bracket on 4, and then we can color in between. So graphically I'm saying any number in the set of numbers between -1 exclusive and 4 inclusive can be used. In set builder notation, all you would do is translate this to the symbols with the less than or greater than. So it would be -1 less than x, which is less than or equal to 4, and then surround it with the fancy set builder notation, which is putting in front of it brace x such that, and then close the brace at the end. Yeah, you're doing inequality notation, and then you make it fancy with set builder. And it's just saying all of x is such that x has these elements, which is between -1 and 4. If we try B, this time again, I like to do the graph first because I just think the graph is easier. We're going to go to positive 2.5, and it has a bracket, so I'm going to include the bracket as if it was the filled-in dot that you're going to be used to from other classes. But we're still just going to go to 4. So we have this tiny little interval here. These are the intervals of numbers represented by the set of numbers from 2.5 to 4 inclusive. And if we were writing this in set builder notation, like I said, I like to start with the actual inequality, which means I'm going to do 2.5 less than or equal to x, less than or equal to 4. And then I'm going to put the little braces surrounding it and then the x such that in the front. We're saying all of the x's we can use, if only, such that is between 2.5 and 4 inclusive. Now this last one says from -4 to infinity. Okay. If we go from -4, am I going to use a parentheses or a bracket on my number line? Parentheses. And then I'm going to color all the way to infinity, which is all the way to the end of the graph. And I like to keep coloring like my arrow in that color so I know I intended to go off screen, right? Now, how do we do the actual set builder notation here? And we're going to do it in 2 steps. If you can bypass these steps if you don't need them. But I'm going to still do, like I said before, where I put the first number less than x and less than the second number. But we don't actually include infinities in this process. So I'm going to erase, which I'm just going to mark out for your notes so you can see that I'm erasing it. I'm going to erase the infinity side because I don't want to include infinities in set builder notation. And then I do set builder. So I'm going to surround this. I'm going to go x such that. But now I want to flip this around because -4 less than x with nothing on the other side. It's not a compound inequality. Kind of looks weird. So I'm going to actually flip this around so that it says x greater than -4. Do we see how I just flipped this around so the x comes first and I flipped the sign? But the orientation of the sign is the same. It was open mouth towards x. And it's still open mouth towards x. Just make sure that that's the same so you don't accidentally flip the sign and change it when we're just rewriting the sign in a different order. Yes? Okay. We feel okay about set builder and graphing these inequality lines, right? All of the problems we eventually solve when it comes to inequalities, I'm going to ask you to graph it on a number line so we get the number line thing. Yes? So if we go into more things about sets, and I know that this type of math is not something really covered in a lot of your classes. You touched it a little bit, I think, in geometry, but that's been a while. But we have what are called intersections and unions of basically like sets of numbers. So A intersect B, this notation right here, which may be new to you, A intersect B or A intersection B, is the set of elements common to both set A and set B. I love thinking about these things in terms of a Venn diagram. Let's say you have set A and you have set B. A intersection B or A intersect B is the part of the Venn diagram where they overlap. We're meaning we want the things that are both in A and in B at the same time. Does that make sense? The other thing is called a union. A union B is a set of elements in set A or set B. Basically, I want both Venn diagrams together if it's in A or B, but we can't repeat anything. You've used this symbol to talk about multiple sets of intersections before. Not intersections, intervals, sorry. In Algebra 2 or Pre-Cal, when you were telling me like maybe where the function was increasing and you had to be like, it's increasing here or here or here. And so you had like parentheses, union, parentheses, union. You were telling me it's 3 different sets of numbers put together. It's the same symbol. So if we were going to write A union B, we would consider everything in A and everything in B, but not double repeating the things in A intersect B. So if we see what this looks like when it comes to doing this with intervals, we're going to graph the intervals from -4 to 4. I'm going to do that in red. And 2 to 8, I'm going to do that in blue. And then use those graphs to find the set. But we're also going to fix my typo that I made, that I noticed after I printed everything. This number 1, ew, it should be number -4. I'm so sorry. I didn't notice that before I hit print. On B, I just already know that that's coming, and that was just a classic mistake. Okay, so for this first graph, for the first one given to you, the number line, we're going to plot -4 to 4. Do I use parentheses or brackets on this number line? Parentheses. So I'm going from parentheses on -4 to parentheses on 4 and everything in between. That is set A. It's the first set of numbers we're working with. On the second number line, let's plot 2, 8. Bracket or parentheses? Bracket. Makes sense, right? We like this because before we had to make like open, close circles. It's a closed circle from another textbook, but for us, we're going to use the brackets. They mean the same thing. So I have these 2 sets of numbers. We're considering the set of numbers from -4 to 4 and the set of numbers from 2 to 8. What we're going to do first in letter A is graph them where they intersect. So where they both exist at the same time. Don't do this because the highlight, I can erase my highlighting and I know that you can't. So just watch for a second. If I go ahead and basically like overlay these 2 graphs on top of each other. So from -4 to 4, again, don't do this, just watch. And I overlay from 2 to 8. Where are my colors overlapping? From 2 to 4. What kind of ending point is at 2? A bracket or parentheses? What kind of ending point is at 4? We're going to have to keep that information there. So what I would do is I would say, okay, the intersection is just going to be the places where these colors overlap. So my actual answer here, and you guys can write this part down, is just from 2 to 4. 2 has a bracket, 4 has a parentheses. That's the places they have in common. So my solution set here, if I was rewriting it just as the intersection, would just be from 2 to 4. That's the places they have in common, the intersection. Does that make sense?
Yes.
Now the reason I immediately knew this was a typo is because if it's actually written with a -4, what's the only thing that changed from answer A to answer B? The sign in the middle. The one that's upwards like this, what is that called? Look at your notes. Union, very good. Union means or. We want it to be in this or that with no repeats. So again, I'm going to do double colors because I can. You may not need this later, but I think it's helpful. So if we have from -4 to 4 and everything in here, okay, cool. And then if I overlay that with 2 to 8, if we're counting everything, where does it start? Where does it end? And you're going to leave those particular symbols there, which means, just to make this look nicer, what we would do is we'd go parentheses from -4 all the way to 8, but 8 has the bracket. That's everything without the double repeats. So we would say as an, you can write that down if you want now. We would say as an answer, the union of these 2 sets is the interval -4 to 8 inclusive. Numbers. Yep. I'm giving you a visual answer, but yes, don't overthink set notations and unions and intersections. If you can visualize a number line in your head, you don't have to do all that work. Just might help to see it once or twice overlapping. Okay, so now that we've gone over the number line situation and talked a little bit about sets, when we're solving inequalities, because an inequality is not just one answer, we're not like x is 5, we're saying x is all of the numbers less than 5. We are going to graphically show our answers, so we've done practice for the intervals that we're going to be showing. Don't overthink this. In fact, first day of school, you guys solve some inequalities. Same rules. I've changed none of them because math is math. We're going to solve by isolating the variable. Just remember, again, that if you multiply or divide both sides of an inequality by a negative number, you have to flip the inequality sign. It's the only thing that's different from equations to inequalities. Otherwise, all of the rules from equations work for inequalities. So we're solving that first one. There's only one term with x, and it's on the left side of the equation. So we're going to move the 3 to the other side just to get the x isolated. So that's subtracting 3 from both sides, and I end up with negative 2x less than or equal to 8. What's my next step? By what? Negative 2. Your spidey senses should go off. If you said divide by a negative, you have to flip that sign when you do that division. Otherwise, you're giving me the wrong set of numbers. I like to draw a little woo when I flip my inequality sign because it's fun. So we have our inequality here. But what I want us to also get in the habit of is showing me graphically what this means. So graphically, when we make a number line, if one is not provided for you, I don't really care how many tick marks you show me. Just show me numbers around the number that's important. Meaning, if this is negative 4, this would be negative 5, this would be negative 3, this would be negative 2. Give me a number line with numbers surrounding the number we care about, or numbers we care about. And if we're saying that all my solution set is all numbers that are greater than or equal to negative 4, then what I'm going to show in my number line is I'm going to show including negative 4 and all of the numbers larger than it going off the screen that direction are my solution set. If we were writing this in interval notation, this would be negative 4 with a bracket, comma, infinity, parentheses. Does this sound familiar? Things we've done before solving inequalities. Let's do one more just to make sure we got it and we've got the plotting of the number line. Okay, we have two variables here. Let's move them all to the left side and let's move all the constants to the other, which means I'd have 2x, I'll show a little bit more work, minus x greater than, and I'm adding that 4 to the other side, and then plus 5. So we just, boop, crane method, move things to the opposite side of the inequality sign. We combine our like terms. And what do we divide by? Negative 3. Now negative 3 again, whoop, flip that sign. See, look how fun that little twirly sign is. And then we get negative 3, hooray. So that's our solution. We just need to make sure we can graph it so that we visually see all of the numbers that are going to be included in the solution set. And again, I don't really care how many numbers you give me as long as you give me a good amount of numbers here. So I know this is negative 3, this would be negative 4, this would be negative 2, this would be negative 1. Sometimes I like to go all the way to 0 just because that's a really sturdy stopping point. But if we're trying to give me numbers that are less than negative 3, that means we're going to go to the left side of this number line, starting at negative 3 with my parentheses this time, and moving downwards towards negative infinity on this number line to show numbers that are less than negative 3. And so a solution set gives me multiple answers that would answer the inequality. Anything that's less than negative 3 without including negative 3 would solve this equation. Now, like I said earlier, all of the rules of equations fit for inequalities, which means if we get an inequality like this, what were the rules we used when it was an equation and it has denominators? We got to find a common denominator here. Between the denominators 4, 3, and 4, what's a common denominator? 12. So if I make my denominators 12, just like we did when it was an equation, we're going to be able to solve this inequality. That first fraction, what do I have to multiply it by? 3. So this is going to be 3 times x plus 3. The second inequality, what do I multiply it by? 4. And the last inequality, what? The last fraction, that's the word I was not saying right earlier. What do we have to multiply that one by? The denominator was 4. 3. Okay, yeah. Even though there's only just like a number in the numerator, we're still multiplying that number by 3. Once the denominators are all the same, I can take the numerators off. This becomes 3 times x plus 3, greater than or equal to 4 times x minus 2. I can't out myself. That one's just 3. 3 times 1, 3. Not a thing is different from when we were solving equation versions of this. It becomes 3x plus 9, greater than or equal to 4x minus 8 plus 3. We combine all our like terms on their respective sides. So I'm going to do 3x minus 4x greater than or equal to negative 9 minus 8 plus 3. Again, as much as you can do in your head, or if you solve a different way, cool. We're solving equations. This is negative 1x greater than or equal to negative 9 minus 8 is negative 17 plus 3 is negative 14. We divide both sides by a negative, so we remember, flip our sign. So we have our solution being all of the numbers that are less than or equal to 14. So we draw our number line. Again, I don't care how many numbers surrounding 14 you give me. If a number line is provided, like, awesome, use the correct part of the number line. But if it's not, just give me numbers that make sense. Are we using a parentheses or a bracket? Bracket on 14, and then it says that it is less than. So if we're going less than, we're going towards 0 and then towards negative infinity to be less than 14. Now, just like with equations, there are times in an inequality you'll have no solution or all real numbers as your solutions, but they're a little bit more obvious, I think, than when that happens for an equation. If you attempt to solve an inequality that has no solution, you will still eliminate the variable and obtain a false statement such as 0 is greater than 1. Well, 0 is clearly less than 1, so that would have no solution. And if you attempt to solve an inequality that's true, you'll eliminate the variables and get a true solution like 0 less than 1. That's true. And so we have these two options for our special cases of no solution or all real numbers. So let's quickly see what that might look like in practice. So this first one we have to distribute to get rid of our grouping signs. That's 2x plus 8 greater than 2x plus 3. The 2x's are the same on both sides, so I would cancel them out, and I'm left with 8 greater than 3. Is 8 greater than 3? That's a true statement, which means how do we answer this question? We would say all real numbers would solve this inequality because 8 is greater than 3. So no matter what I plugged in for both of those x's, they would always have the left side bigger than the right side. And if we see just basically the opposite for b, I see that there are positive x's on both sides. If I subtracted them away, they'd go away. And I'm left with 7 less than or equal to negative 2. And is 7 less than negative 2? No, that's a false mathematical statement. So we answer no solution. Now here's something that might be new to you, so I'll slow down, I promise. Okay, compound inequalities. Let's say we're solving two inequalities at the same time, and they're essentially the same, except that they have the word and in them, and potentially like an opposite sign, like we've isolated, separated, and solved them in some way. Ooh, preview. We can do these as what's called a compound inequality. So if there's a portion of two inequalities that is the same, 2x plus 1, 2x plus 1. We can write that as a compound inequality, and we can actually solve this from the middle out. So from the inside out. We're still trying to isolate the x, but what we do to the x terms in the center, we do to both sides of the inequality, which feels bananas. But here, let's go. Let's isolate the x in the middle here. Okay, if this just had, don't do this because you're going to regret marking your paper up like this, but if it just had this, what would you do first to solve for x? Move the 1. Okay, that's what we're going to do. And how do we move that 1? Adding or subtracting? I'm actually going to show my work here because I want you to see that we are going to subtract 1 here. We're going to subtract 1 here. We're also going to subtract 1 here. Inside out, we do it to both sides. This becomes -4 less than 2x less than or equal to 2. Now again, if this part was missing, how would you solve for x? Divide by 2. And that's what we're going to do again. I'm going to show my work again because I think it's important to see this. We can do it all the way around it because we're solving 2 inequalities at the same time that are just smushed together into this compound inequality. So we're left with -2 less than x, which is less than or equal to 1. That is a solution set for a compound inequality. We can solve from the inside out. Now, of course, we can also graph this guy on a number line. Again, give me numbers that make sense surrounding these terms. So here I've got from -2 to 2 just to like show a number line. And we're going from -2 exclusive, so with the parentheses, to 1 inclusive, which means the bracket. And everything in between is a part of my solution set. It feels weird to solve an inequality that way from the inside out. But what it's going to do is going to allow us to, one, save paper because we don't have 2 inequalities floating around with the same exact steps for solving. And it combines to an interval anyways, to an inequality with a beginning and an end, just like when we started this lesson out. Questions about that before we flip our page? So the reason we want to solve these compound inequalities is when we get to inequalities with an absolute value sign. When you guys solved absolute values with an equation, the steps were isolate, separate, solve. You can sort of think of these the same way, except we have to qualify this with what type of inequality we're working for. We still want to isolate the absolute values first, so that we're still doing the isolate step first. However, once we get here, we need to make a choice. If we have an equation that says less than in it, so we have our absolute values isolated and it says less than some number, that is considered a compound inequality with the word and. And here's how I remember this, and this is just so silly because it doesn't actually make sense, and I've said it out loud before, and people are like, I guess, Miss Quigley. You see the less than symbol? This is like saying this is less than. It's an and statement. It's a less than. So it's an and statement. And statements are solved with a compound inequality. So when we isolate, separate, the separate step is separating into a compound inequality instead of 2 separate equations because it's less than and less than. Okay, let's say instead when you isolate the absolute value, you have a greater than sign. This is considered to be an or statement. So I'm going to misspell the word greater on purpose, right? Because this is supposed to be or, greater. Okay, greators are your or statements. Less than are your and statements. And if you have an or statement, you don't get to combine them into a compound inequality. You do just have to keep them isolate, separate, and solve into 2 separates. But notice when we isolate, separate, and solve, this was where we started. We had to flip the sign and flip the inequality. So the separate step gets a little bit complicated there where you flip the sign and flip the inequality, not just flip the sign like a regular equation. Let's see some of these in practice so we can see what happens. Okay, so we got a basic one right here. It's already isolated. What type of equation is that? Is that a less than or greater than?
Less than.
Less than. So if we misspell that, so this is less than. This is going to be an and statement, right? We're going to make a compound inequality. So what we can do is get rid of the absolute value bars, and we would say x minus 4 less than 3. But then we're going to go to the front side of this inequality and put the -3 there as well. Notice I use the same symbol. Technically, it flipped if you wrote it the other way with the x minus 4 first. So it's not doing anything different. We're just writing it as a compound inequality. Since this is a compound inequality, we can solve from the inside out. What would I do on all sides? Plus 4. And I'm going to show my work again because I think, especially for this concept, it'd be helpful to see all of that because we're adding plus 4 everywhere. This becomes 1 less than x less than 7. And ta-da, we're done. We would draw a number line to make our answer fit on a number line. Here's 0, here's 1, 2, 3, 4, 5, 6, and here's 7. I'll give you one more accurate 8. Okay, all right. I walked right into that one, didn't I? I know it's my age showing, but I honestly don't get why that's funny.
I think it's just funny because of how stupid it is.
Okay, I accept that. I saw some like football guy give an interview and he said 6'7" in the middle of it. It's like a coach of a team. And nobody in the press conference reacted because everybody's my generation or older and everybody's like, I don't get it.
I don't think there's nothing to get. I think it's just like so dumb.
Okay, I accept. I just like, I want to make sure I'm cool. Okay, I just want to be included. All right, so here's my question. What kind of inequality is this right now?
1, 0, 2.
Greater. So would we confidently say this is going to be an or statement?
Yes. Wait. No, because of the line, and then you don't know if it's a negative or it's a divided.
Correct. We have to isolate the absolute value first before we make our less than or greater than choices for how we solve this. So what I'm going to try to do first is get the absolute value bars by themselves. To do this, I'm going to subtract 7 first. So this is not compound inequality right here. We're just regular isolating the absolute value bar. So if we subtract 7 from both sides, we end up with negative 20 on the right side. What would be my next step? To isolate the bars.
Distribute?
No, we can't distribute inside the bars.
Oh.
But-
Subtract 2. What's
The 1 you haven't said yet.
divide?
We're going to divide by negative 2 because it's currently multiplied by that absolute value. So the opposite of multiplying is dividing. So, we're dividing by a negative, right? We have to flip our sign. Dividing by a negative, you flip the sign.
So if you divide anything in the equation,
Why was I asking that question?
A negative. If it's positive, leave it alone. Cadence, what was your question?
You just divided by -1.
Yeah. But now that the absolute value bars are isolated, that's when we ask ourselves, is this an or an and statement? What kind of symbol is it now? Less than. So we still know that this is a less than symbol, and we're going to be able to solve a compound inequality because of the and statement. Again, the way I make sure I've set this up right is I write down the regular inequality without the absolute value bars. Then I go back to the front of it, and I add the negative 10 in the front so that I'm solving the correct compound inequality. What's the first step here? Subtract 5. I'm not going to show my work this time because I think we got it. Subtract 5. Subtract 5. Last step. Divide by 3. Negative 15 divided by 3 is negative 5. And 5 divided by 3, we're going to leave as a fraction, 5/3. And so, boom, the x is isolated. There's our solution set. All we have to do is graph it.
how do you graph 5?
That's such a good question. I'm so glad you asked. Here's negative 5, 4, 3, 2, 1, 0, 1, 2, 3. So if we were going to graph 5/3, where does it go? How many times does 3 go into 5? Once and a little bit extra, right? How much extra?
1.
2/3. So we're going to go most of the way between 1 and 2 because 5/3 is a little bit more than halfway between 1 and 2 because it's 1.6 repeated. 2/3 of the way. And then, of course, we have our negative 5. And so, boom. When it comes to plotting our fractions, I need it to be in the correct area. And unless you're given a number line with the right units to graph it perfectly, just get it close. Would you like number lines? Okay, I'll consider it. Okay, let's do just one more. This one looks super weird because the absolute value is on like the other side, right? And I know that that makes a lot of people uncomfortable to have the thing you're solving for on the right side. So let's just go ahead and flip this around so that it's the way you guys like it. So I'm just going to put the absolute value bars first and the 7 second, which means what should I do with that symbol? Yeah, open mouth should still be towards the absolute values, which is flipping it, but we're just rewriting it, making sure the orientation of the symbol is still facing the large and the small side correctly. Is the absolute value bars, are the absolute value bars isolated? What kind of inequality do we have here? Yeah, because if you did it up at the top, technically we're still saying the absolute value is greater than 7. You have to read it backwards, which I find confusing for most people. So if we write it with the absolute value coming first on the left side, just reorienting the symbol, make sure that you've read it correctly. I didn't change anything about this problem. I just rewrote it into a way that maybe is a little bit easier to read. But this is a greater statement, greater, which means what we're going to do is put the word or in the center of our problem. When we separate this, instead of creating a compound inequality, you're going to have one of the absolute value bar with numbers gone. Easy peasy, just write it down. For the other one, you write down the things from inside the absolute value bars. Flip the sign, meaning this is going to be less than and -7. We're not solving a compound inequality this time. We're solving two separate inequalities, and we're going to stick the word or in between them. So if we solve these, the first step we would do on either of them is still subtract 5. This is -12, and if we subtract 5 over here, that's 2. I feel like I'm doing every step at the same time, giving the vibe of the compound inequality. They're just actually separated. Put the word or in between them. We're dividing both of these by -2. Divide by -2. I'm going to flip my sign again. So -12 divided by -2 is +6. And if I flip that inequality sign as well, 2 divided by -2 is -1. My solution is x greater than 6, or x less than -1. Now, what would that look like on a number line? Great question. So glad you asked. Here's a number line that's going to include these numbers. So I'll do like here's 0, here's -1, here's -2, 1, 2, 3, 4, 5, 6, here's 7, here's -3. Okay, so it's just like a general number line. This one had to be kind of aggressively long because these numbers are a little bit far away from each other. But we have to plot both inequalities. The first one says x should be larger than 6. So that means I'm going to go to 6 and I'm going to color in all of the numbers that are larger than 6. The second inequality says that I need all of the numbers that are less than -1. So I'm also going to go to -1 and color in all of the numbers that are less than -1. What do you notice about our graph that did not happen in any other graphs?
Nothing.
Nothing like overlaps? Okay, what else?
There's a gap.
There's a gap because they're going off one side to -infinity, one side to +infinity. When you have the or statements, because there's two statements not put together, you should have two sections colored on your number line. Because it's like this section or this section works. Compound inequalities are like stuck on the inside. They have ending points and we're coloring in things in the middle. Or statements are like coloring things on the outsides. Does that make sense? Okay, so less thans and greaters. I know it's not English, but it makes a lot of sense to me. Less than and greators.